Welcome to Chemistry Masters. Friends, today's topic is disconnection approach. Disconnection approach is one of the most important part of organic synthesis. So let us begin and understand what disconnection approach or retrosynthesis is. So whenever we talk about disconnection approach, we are understanding or we are talking about retrosynthesis. So friend, as the name or the word retrosynthesis suggests that it is opposite synthesis, means in this we are going to break the target molecule into the simpler one, or you can say in synthesis generally what we do, we make a product from reactant, while in retrosynthesis we break that product to its initial reactant. Now it should be known to us, or it should be understood to us why retrosynthesis is important. So whenever we talk about retrosynthesis, or retrosynthesis actually provide us some alternative pathway which can be selected for generation of target molecule, or from retrosynthesis we can understand that how any target molecule can be synthesized by some cheap and easily available chemicals. So friend, going further into disconnection approach or retrosynthesis, there are certain points which should be known to us. So the terms which are important in retrosynthesis are target molecule, which will be designated by TM in further coming points, disconnection, retrosynthesis, retrosynthetic arrows, synthons, and synthetic equivalent. So we are going to understand all these points with the help of certain examples. So as it is shown that there is a ester molecule which is written as TM. TM means target molecule. Target molecule means that is the molecule which you have to disconnect, or you can say this is the molecule which is being synthesized in forward direction, but in retrosynthesis it is going to be break into its simpler form or simpler molecules, you can say. So wherever we are going to break the molecule, that point is known as disconnection, and disconnection is always shown with a wiggly line. This red line is known as a wiggly line, and you should be knowing that whenever we are going to disconnect the molecule, the disconnection is only mental disconnection, means we actually are not disconnecting the molecule, we actually are finding here that which simpler molecule or initial molecule will be there which can make this target molecule. Now this arrow which is shown here is our retrosynthetic arrow, and whenever you are showing retrosynthesis, over this arrow you are going to show that bond which you are going to break mentally. So here we are going to break the bond carbon and oxygen, that's of ester, that's why we have written CO ester, and this is the arrow by which you are going to show the retrosynthetic arrow, or you can see that it is just somewhat different as compared to the normal synthetic arrow. Now whenever you are going to break this bond mentally, certainly we are going to get two ions. So when you are going to break this bond, the bond is between carbon and oxygen, and we all know that oxygen is somewhat more electronegative as compared to the carbon. That means oxygen will try to gain the shear pair of electron by which the bond between carbon and oxygen has been formed. And when this bond will break, the more electronegative species will get negative charge. That means oxygen will get a negative charge, and this carbon will get a plus charge, like this. So you will get a carbocation and you will get oxide ion. So these ionic species or these ions which are formed in the pathway of retrosynthesis, they are known as synthons. And we all know that all the species which are charged, they are never stable. That means they are going to react with someone. So here in retrosynthesis, what we do, we change these synthons to some stable molecules which are known as synthetic equivalent. So as the example is shown here, the carbocation is added with Cl negative to give you acyl chloride, while this negative species, that is your oxide ion, is added with one proton, that is H plus, to give you alcohol. And synthons are converted into stable species or molecules. Those are known as synthetic equivalents. So you should be knowing that you are going to disconnect the molecule. When you disconnect the molecule, you will be writing the bond which is going to get disconnected over the retrosynthetic arrow. After that, by breaking this bond mentally, you will get some charged species which are known as synthons, and these synthons should be changed to synthetic equivalent by satisfying the charge which are present over the synthons. Now friend, in coming part of the video, we are going to show this wiggly line or disconnection line with the help of another type of wiggly line, you can say. So now it is important to understand that what are the rules or what set of points should be followed whenever we are going to disconnect any molecule. So there are certain set of molecule when we certain set of rules when we are going to disconnect the molecule. So first rule is that we should be knowing that in the target molecule where there is whether there is any functional group or not. If there any functional group is present, then we are going to disconnect the molecule near about it only. The second rule is that whenever any molecule is having any heteroatom in it, then you are going to disconnect the bond next to the heteroatom. So this point or these 2 points will be understood by the coming example. So you can see that in this example we are having one functional group, that is ether. Ether do have carbon oxygen linkage. So we are having two carbon oxygen linkage. One carbon oxygen linkage is between the carbon of the benzene ring and this oxygen, while another carbon oxygen linkage is on the other side where the CH2 is added with or it is joined with oxygen. So we are having two carbon heteroatom bonds. Now what we have discussed in the point 2, that we should disconnect the bond next to the heteroatom. That means we can break whether bond between the benzene ring and oxygen, while we can do what, we can break the bond between CH2 and oxygen. So here they are shown with two wiggly lines as option A and option B. Now we will see that how these bond can be broken and what synthetic equivalent you can get. So we will understand both of them one by one. So according to rule, if we break it according to our mental disconnection A, so what will happen? Oxygen is more electronegative, that's why oxygen will get a negative charge, and the carbon of the benzene will get a plus charge. And as we are going to break the bond between carbon and oxygen, that's why we should write over the retrosynthetic arrow CO, and you can write ether along with that. And as we have said that oxygen will get a negative charge and carbon of the benzene ring will get a plus charge. So these two will be your synthons, and synthons should be changed to the synthetic equivalent by satisfying the charge with their counter ions. Means plus should be added with any negative species like chlorine negative, or maybe some other negative species can be added, while negative charge should be added with a plus charge. Here we have added proton to it to satisfy the charge. So this is how when we are breaking the bond between benzene ring and oxygen, then we will get these two synthetic equivalents. Now if we break our this carbon oxygen bond according to our mental decision B, then what you get? So when you break the bond between carbon and oxygen by mental disconnection along B, then you get again two synthons Again oxygen, which is more electronegative, will get a minus charge, and the carbon, which is electropositive as compared to oxygen, will get a plus charge. And again we have said that these are synthons. Synthons should be satisfied with their counter ions. So along oxygen, which is negative, you can add any hydrogen so that you can get OH out there, and to plus you can add any negative. So here you can see that when you break it along A, the synthons are somewhat different, and according to that the synthetic equivalent also are different, and when you are breaking it along B, again the synthetic equivalent which are obtained to you, they are different. These were the first two rules of disconnection, in which the first tells you that there should you are going to disconnect the bond next to any heteroatom. Now the another rule is that whenever you are going to disconnect the heteroatom and carbon bond, you should not break the bond between aromatic ring and heteroatom in priority. That means the bond between heteroatom and benzene ring or any other ring should be broken if there is no other option. So again we can take the same example. We have said that the bond A can be broken or bond B can be broken according to the earlier rule. So in this rule you can see that when the bond between according to this rule, we can't break the bond between benzene ring and oxygen. Okay, or you can say the mental disconnection A is should not be a priority for us. That means the bond breakage according to our mental disconnection B should be taken on, or it should be given priority. So when we break it along B, then you get those two synthons in which oxygen will get a negative charge and the carbon CH2 will get a positive charge, and synthetic equivalent can be obtained by satisfying the charge with counter ions like this. So in this rule we have said that we should not break the bond in priority that is attached with a ring. Now the next rule tells you that the disconnection of reactive group should be done at the instant, or it should be done at the first priority. So that can be understood by the following example. In this example you can see that we are having two functional group. One is amide CONH, and while another one is ether. Now we can disconnect either this functional group, that is our ether, or we can disconnect the amide in priority. So which one will be broken at the priority, that will depend upon their reactivity. So as we know that nitrogen is more basic as compared to oxygen. That means nitrogen can donate its electron more easily as compared to oxygen. Okay, so oxygen, which is more electronegative, will not try to donate its electron very easily. That means its reactivity will be somewhat less as compared to nitrogen. It suggests that the bond next to nitrogen should be broken in priority as compared to the bond between carbon and oxygen. So our third rule shows that you should not break the bond according to the mental disconnection A. In place of that, you should be breaking the bond between carbon and nitrogen according to the mental disconnection B. So whenever you break the bond B, you get plus charge over the carbon of carbonyl and negative charge over the nitrogen of amine, and these two charges can be satisfied with their counter ions like this. Now what we have done, we have broken the bond between nitrogen and carbon, and we have disconnected the more reactive species at the first. Now we are having the another functional group, that is ether. Now we have already said that in ether we are not going to break the bond between the ring and oxygen according to the previous guideline we have discussed. So what we are going to do, we are going to break the bond between the carbon and oxygen according to our mental disconnection A. So whenever you will break it, so oxygen will get a negative charge and the carbon next to it, through which we have disconnected the bond mentally, will get a plus charge, and those can be satisfied with their counter ions, and we will get phenol and another species like this. So this is how you are going to disconnect any molecule which contain more than one functional group, and in that we should be remembering that the more reactive species should be disconnected first. Now one of the most important point that should be remembered here, that the species which is disconnected first, it should be reacting in the forward direction reaction at the last. That means the synthetic equivalent you have got at the last, they will react first to give you some reactant, and that reactant will react with that species which we have disconnected at the first. Now the next rule tells that disconnection always should give you some reliable reaction, or it should always give you such molecule which are known to you or which you might have seen anywhere in books or maybe in labs or in chemical laboratory. So we will understand this concept according to this example. So here we again have got ester, and we can see that the bond in this uh, species can be broken from number of places. So it can be broken according to mental disconnection A or maybe mental disconnection B. So we already have said that the bond next to the ring should not be disconnected. Okay, that means the bond disconnection between carbonyl carbon and oxygen should be there, which is attached to the benzene ring. Means this disconnection will provide you two synthons in which the carbonyl will have a plus charge, carbonyl carbon will have a plus charge, and the oxide ion or phenoxide ion will be formed. This phenoxide ion can be converted to phenol, which we know that this can be easily obtained to us. This is one of the known molecule, while the another one which has been obtained here is propanoic acid, and we all know that propanoic acid can also be obtained very easily. So you can see that we can disconnect a molecule in such a form that two species which we are getting, they should be known to us, or the reaction which we are taking on, that should be reliable, that should be known to us. Okay, or here you can see that we are disconnecting ester into its reactants, which are acid and alcohol. Okay, here it is phenol, so it is de-esterification reaction, and if you are going to carry this reaction in forward direction, acid and alcohol together will react to give you ester, and it is a esterification reaction. That means it is a reliable reaction. Now one another point which should be known to us, that if you have got a positive charge on the carbonyl carbon, you can satisfy that charge with number of species, okay, which are shown here, and it should be known that the species which we are adding, that should be very easy to go in the forward direction. That's why you can do what, whenever you are getting a plus charge over the carbonyl carbon, you should add any halide to it in preference, so that in forward direction or reaction we can remove that halide very easily. In spite of that, you can add ester or something else also to uh, make that reaction somewhat faster. Now the retrosynthesis and synthesis of certain molecule should be is being taken out here to make you understand that how retrosynthesis is done, and how its synthesis or its normal synthesis can be done. So we have taken again one example, that is of ester. We already have said that when you are going to break the bond in ester, you should be breaking it between carbon of carbonyl and the oxygen next to it in this fashion, that carbonyl carbon will get a plus charge and oxygen will become a negative charge species, or oxide ion will form. And after that, what we can do, we can satisfy the charge to give you acyl chloride, or maybe you can have OH here, or maybe you can convert it to ester it also. While to the negative we have added hydrogen, which is one of the most common counter ion to be added to any negative species. Now these two synthetic equivalent which has been formed in this retrosynthesis reaction, they will react to each other in synthesis part. So here you can see that how they will be reacting. So in this reaction or synthesis part, you can see that the oxygen is having lone pair of electron, and oxygen here will act as a nucleophile, means it will attack at that species which is having leakage of electron, which is having less electron, or which is somewhat electropositive. So oxygen will donate its electron to the carbon of this carbonyl, because the electronegativity difference is there between carbon and oxygen. That's why the shared pair of electron will be somewhat more towards the oxygen, and carbon will have somewhat electropositive character. So the movement of electron will be somewhat like this. The oxygen will donate its electron to the electropositive center, while the bond between carbon and oxygen will break in this fashion to give you oxygen as a negative species, and the bond between oxygen and this carbon will be formed, which is shown here. And you can see that oxygen is donating electron, that's why it will get a plus charge. Now any species which is having plus or minus charge, or it is having certain charge over it, the species or that molecule is unstable. That means to become stable, that ion or that molecule has to lose its charge. So here what happened, the negative charge will go again to the carbon to which it is attached, and in turn the chlorine will be removed. So to give you in such fashion, that Cl will be removed, O will come back to give you carbonyl, and again you can see that here is O plus, which is unstable. So hydrogen here will donate the electron to become H plus, and oxygen, when it get an electron, it will become neutral to give you the target molecule, and removal of HCl will take place. So this example shows you that how retrosynthesis or mental disconnection of any molecule can be done, and the synthetic equivalent which are obtained out here, they act as a reactant in forward direction to give you that target molecules. So the main thing about this topic is that we have to understand how a particular molecule can be disconnected mentally to give you the simplest molecule which you can use in your lab to actually synthesize that molecule. Okay, so this was all about this topic. So in coming videos we are going to talk about more regarding retrosynthesis and disconnection approach. More rules about them will be discussed with some more examples. To friends, for any suggestion and query, you can mail us over chemistry.master.19@gmail.com. You can subscribe us, you can like our videos. Thank you.